Hi, hello and welcome to the Chemistry 106 lab on gas laws. So gases behave differently from the other two states of matter, and they can be most easily manipulated, most quickly manipulated, because of the large distribution of atoms in a gas. So gases are extremely susceptible to changes in temperature or changes in pressure. Now, we're familiar with changes in temperature already. We either add heat to raise the temperature, or we put a substance into ice in order to lower the temperature. But pressure is forces against matter, okay? Pushing against it. So when you say you're under pressure, there's a literal facet to that there are forces pushing on you from outside. When you scuba dive, the pressure of the water is why you can't go too deep, because it would crush you. It's one of the reasons why when you fly, you may have to re-equalize the pressure in your ears by holding your nose and blowing, because the reduced pressure on the outside, you need to equalize on the inside in order to function and feel normal. So temperature is independent of location, but pressure always requires a container, okay? Because pressure is in a defined space. Temperature is too, but temperature has a gradient that extends out. So if you have a central area that's hot, then you have an area around it that's medium, and then a central that's low, and then everything out here is none. Okay, so there's a gradient of heat, but pressure is only once it's contained inside of something, and then we have collisions with the container caused by the particles of that gas inside the container, and the collisions are synonymous with the pressure against the container. So that's how we measure the pressure of a gas, is by putting it into a container. So generally speaking, anytime we're manipulating the pressure of a gas, we have to work with a container. And the container is usually sealed. That's to maintain the pressure. For when we do Gay-Lussac's law, we're going to show you that there's an exception to that, and that's because of the container that we have it in order to be able to tell once it's actually ready for the reaction to occur. So other features that affect gases are N, which is the number of moles of the gas, and V, which is the volume. Okay, and these can all be manipulated. I can change the temperature, I can change the pressure by changing the container it's in. Smaller container means larger pressure. I can change the number of moles by either removing gas or adding the gas, and I can change its volume, again, usually with a container. Because once you release a gas from a container, it will immediately fill whatever volume it enters into. So if you open a container of gas inside of a room, the room now becomes the container, and the gas will expand to fill the volume of the whole room. Okay, things like, if you've got a rotten egg and you open it up and it fills the room and the house, and you've got to open the door to air it out, that's because opening the door opens the container, and then the gas disperses into the new container, which is outside. Okay, so in this lab, we're going to look at 3 different laws. Gas laws. The first one we're going to look at, and we're doing them in this order so that when we look at the exercises, they're in order, is Boyle's law for gases. Now, Boyle's law teaches us that volume is inversely proportional to the pressure. Okay, so if you put pressure on it, it restricts it. So and that works for anything. You squeeze on a lemon, its volume gets smaller. If you squeeze on a bag, its volume gets smaller. And that's because what happens is the gas that's inside the bag is compressing as you put pressure on the bag. So if you've never done this, grab a bag of potato chips that's still sealed, and if you push on it, you'll see that you can actually make it feel smaller, and that's because there's a significant amount of gas in the bag, usually nitrogen, to keep the chips fresh. But you're compressing that by putting pressure, therefore its volume decreases. Contrarily, if you relax the pressure, the volume will also increase. Okay, so what we're going to do is we're going to And again, this is only with the gas. So in our exercise, the gas is air, and we're going to put it inside of a container that's compressible, and it's going to be contained underwater. Because we can compress water easily with our hands by pressing on a container, and then that force will be transferred from the water to the gas, and you will be able to see when you push on it that the volume changes. So we'll be building an apparatus that demonstrates Boyle's law. Okay? In the second part, we are going to be looking at Charles' law. Charles' law. These are named after the individuals who found them. Okay? And Charles' law teaches us that the volume is proportionate to the temperature. Okay? And this has to do with energy. As the energy of a gas increases, its activity increases. If its activity increases, it moves more. If it moves more, it will try to occupy a greater volume. If you decrease the energy, the gas will move less, ergo it will occupy less of a volume. So what we're going to do is we're going to set up an experiment in a container. This will be a solid container inside of a glove. And we are going to fill the glove with a gas that we create by a chemical reaction, and then we're going to put it onto heat, raise the temperature, then we are going to put it into ice and lower the temperature, and then we are going to let it equalize out by putting it on the bench top, and observe the changes in the volume as the temperature of the gas changes. Then finally we're going to look at Gay-Lussac's law. Okay? And Gay-Lussac's law tells us that the pressure, the relationship between the pressure over the temperature equals the pressure over the temperature. Okay, so what does that mean? It means if I have a gas that has a pressure in a container that's at one temperature, if I change the temperature, the pressure will change the same way. Okay, so if I lower the temperature, I will also lower the pressure. If I increase the temperature, I will also increase the pressure. Okay, so this is the one where we're going to have a slightly open container, and that's because we need to know when it is boiling. And then we're going to move it to an ice bath, okay, which will lower the temperature, which should lower the pressure. Okay, and when you lower the pressure, you have fewer collisions on the inside of the container. Fewer collisions means the container usually gets smaller, because that's what happens. You've ever seen a helium balloon as it gets old, it no longer floats and then deflates, because as the gas escapes from the balloon, there's less in it, and therefore there's less pressure on the container. I know that's a temperature thing, but that's a way to visualize what will happen to the container when we change the temperature. So we're going to be looking at these circumstances and monitoring the behavior of the gases, and then describing what we observe. Now remember, an observation is not an explanation. Okay, so keep them separate. When it asks you to write down what you observe, write down what you observed, and then explain based on the context of the gas law that we're looking at in each exercise, how that has occurred and why you saw what you saw. Now, I've already done the exercises, so I know they all worked this time, and so you will get the information that you need in order to properly define the relationships between the different facets of the different effectors of a gas's behavior according to each of the laws. Okay, with that, we'll move to classroom exercises. Hello and welcome to the Chemistry 106 Gas Law Lab. This is exercise 1, Boyle's Law. So what we have here is a plastic water bottle that I have taken the liberty of filling nearly to the top with tap water, and a test tube that is filled about halfway with tap water as well. What we're going to do here is take these two items and combine them into one, So gently you remove the cap and try and put this in without spilling the water. Okay. Now if you've done it correctly, and this is something you can do at home, you'll see there's an air bubble, an air pocket in the test tube here between labels in the way, but you can kind of see it right there. There's an air pocket from there to there. So Boyle's law is about pressure, so what we're going to do is we're going to gently squeeze the bottle. Don't need that anymore. And then observe what happens to the test tube. Okay, and if you have the amount of air correct in the test tube, when you squeeze the bottle, change should occur. So you need to squeeze the bottle in the right spot. Okay, take note of what happens to the test tube itself and what happened to the amount of air in the test tube. You can see that as I squeeze the top of the bottle. Okay, that concludes exercise A. For exercise B, we're going to turn our attention to the analytical balance here and the setup over here. Okay, so what I have here is an ordinary lab glove, an empty 250 ml beaker, and then I have a bottle of half molar hydrochloric acid. I have measured out 25 mils in this graduated cylinder. And then on the balance here I have as close as I could get to 2 grams of sodium bicarbonate. Okay? So what we're going to do is we're going to take the sodium bicarbonate and we're going to put it inside the glove. Okay? And then we're going to take the hydrochloric acid and put it in the beaker. Okay. Once they've been combined, then we are going to hold this so that the fingers are down here with the sodium bicarbonate in them, and stretch the glove so that it covers the top of the beaker, like so. Okay? Once you've made sure it's tight around the edge, create a good seal, you're going to dump sodium bicarbonate into the acid and record your observations on your report sheet. This is Charles' law. Okay. Also in the hood, I have taken the liberty of preparing both an ice bath and a hot water bath for the next part, because there's 3 things we're going to do to this. So after we've watched the bubbles form in this beaker, we'll move it first to the ice bath and let it sit, then to the hot water bath, and then to room temperature, and observe how it changes over time. Okay, I was hoping that there's still some sodium bicarbonate in there. Look how beautiful that is. It's like giving yourself a high five. Okay. I'm going to pause that and then move to the hood. Right now, over here in the fume hood, we have an ice bath that's been prepared. Now this ice bath here is in this large beaker, and we've just taken some regular ice, and then I've added table salt to it to sort of form. I've also formed it so that a beaker will fit inside it. So we're going to set that in there and then let it sit for 5 to 10 minutes and then measure the effect on the glove. While we're waiting for that, I've also got here the, for part C, the Lusak's law. these ordinary aluminum cans that are full of tap water that are set here to boil, and we're gonna do that to get that ready for part C. Okay, so we'll leave this for 5 or 10 minutes, then we'll come back and check up on it. Alright, after leaving the glove in the ice bath for about 8 minutes, we noticed that there is a slight change in the glove's orientation. Now we're going to put it into this hot water bath behind it and leave it for 5 to 10 minutes. So we'll let that sit, and then we'll come back, and that won't take that long. Now you see. Okay. You can already see that the hot water bath has caused a change in the orientation of our glove from the cold water bath. Okay, so I'm going to let that sit now on the bench top and go back to room temperature and then compare that. Alright, after waiting 10 minutes, we've noticed at room temperature there is a slight change to the glove's orientation. Okay, in just a little bit we'll be ready to look at the Lusak's law once these are fully ready to boil. Alright, we come now to the pièce de résistance, part C, Guy Lusak's law. So what we have on the hot plate are two soda cans with boiling water in them. And you can see it's boiling because you can see a little bit of steam wafting out of this can. And I can tell it's boiling because it's really hot above the hot plate. Then we have this ice water bath. What we're going to do is we're going to take the can and, as deftly as possible, tip it into the ice water bath and then observe what happens to the can. Ready? Perfect. Okay, and I prepared two just to do it twice because, you know, sometimes it doesn't work very well on the first try. And our second one. And you can see what happened to the can. Okay, that concludes the data collection portion for this laboratory exercise.